Okay. So Vitek will have no trouble making the circle.
So should I start?
Yes, please.
Okay, so thank you very much for giving me the opportunity to be here. So this is one of the two talks today. This will be rather an introduction into this abstract Fraïssé theory. So essentially, I would like to start with some very simple examples at the beginning, and then to formulate like the abstract core of the theory using the language of category theory. Now I realize that if I want to draw something on the blackboard, it won't be visible at all. So maybe I'll turn on the light.
Yes, sure.
Okay. So like the very first simple example, the order of rationals. There is the very classic theorem of Cantor, which tells you that there is a countable dense linear order without endpoints. Very classical theorem. How does the proof go? It is a simple back and forth argument construction. Yes, so if I want to draw a image, big of light, and I can't make it. Okay. But maybe. But that is completely invisible. Can you do some better combination? Every row or no?
Te drugie. A górę może zgasić. Much better.
So I guess it's usually blackboard tops here, right?
Yes.
I think that I will need to switch to just one of those. So can everybody read it at least?
Yes.
Okay, yeah, so the proof is very simple. Like this very standard back and forth construction when you have possibly two countable linear orders, and you know that they are all dense and have no endpoints, which means that between every 2 points there is another point. This is the density, and there are no endpoints. So there is also some point here and some endpoint there. So to show that every two such things are the same, are isomorphic, you just enumerate this countable set, you enumerate that countable set, and you start doing the back and forth. You start at the first point, and you somehow assign it to another point. Then you take the first non-occupying point here, maybe it's on the right, and you know that there is a corresponding point here because this is not an endpoint. So you can always realize it's tied here. Then you take a first point here on the top, which was not yet used, maybe it's here. But again, you know that it has a partner on the other side, because again, there is point between these two, because this is dense linear order. So there is another point here. You can assign it like this. So you can just continue, and since you are always taking the smallest non-used point on one side, you will get bijection in the end. So this is like a very concrete example of the simple back and forth construction in this case. And the corollary of this, by the same construction, you have this property of ultra-homogeneity of the countable of the rational order, saying that whenever you have a finite isomorphism between two finite subsets of this rational order, it can be extended to an automorphism. So if you already have two copies of Q, and you already have assigned some finite isomorphism between these two parts, you can extend it to the automorphism of the whole structure, which is again easy. You can just do the back and forth construction inside. But the point is that this property is called ultra-homogeneity. This is just one particular example of structure with that. Moreover, it is also easy to see in this case that every countable linear order embeds into the rational. So it is universal. That is another important property. So this is like one of the very simple examples. So far everything clear completely. So let us continue with another example. The random, or also called Rado graph. So there is this theorem, standard theorem, proved by Bartoš and Remy, that if you take omega, countable infinite set of vertices, and between every two vertices, you either put edge or not, and you just toss a coin. So you put there the edge with probability 1/1/1/2. If you construct a graph like this, or sample a graph like this, then the result is that almost surely the resulting graph will be isomorphic copy of one particular graph. There is one particular graph such that with probability 1, you will always get this one, an isomorphic copy of that. This particular graph is characterized by the following property. You have your countable infinite graph, and whenever you have two finite disjoint subsets of the graph, there is always a vertex, other vertex in the graph, which is connected to all vertices from one set, but to no vertices from the other set. Just like on this picture, someone prescribes you these two sets, and you can always find a vertex outside which is connected to everything here and to nothing there. This is the characterizing property. The point is that you can view this property as a one-point extension property. That you have a finite subgraph of your random graph here, and this specification that you want to be connected to every point here and to no point here, this is the same thing as giving you a one-point extension which lives outside. You have this graph and you embed it as a subgraph to some bigger graph just with one point, because then this point is connected to some of the vertices here. So it defines some kind of type over this graph, and you want to realize this type inside of this graph. So this property is just complete realization of the fact that whenever I have one point extension outside, it is actually realized inside. This is what I mean by one point extension property. And from this one point extension property, you will actually get the full extension property. So even if you extend this smaller graph by finitely many or even countably many points, it is still realized because you can just continue point by point. So this extension over here, it may not be just one point, it can be even more points, and you can still realize that just one by one. Like abstract, diagrammatically, this is your random graph. This is something small, something finite. You have the copy of the graph, and you have something bigger, some bigger extension. So you just enumerate its points one by one, and you realize this point here by the one-point extension property. Then you realize this point, then you realize that point. And in the end, you extend this embedding, this embedding of this part here to the whole graph. So in particular, the universality for all countable graphs follows just from this one-point extension property. And similarly, you can prove also ultra-homogeneity and uniqueness of subgraph just from this particular property. Now the situation here is that you start with that both these big graphs are the same. It is this Rado graph. And inside you have two isomorphic finite graphs. You have isomorphism between this part here and that part here. And the point is that then you can extend this isomorphism to the automorphism of the whole graph. You are doing the very same thing, but you are switching sides. So in the end, you will have isomorphism here. So this is again just one very classical particular example of this phenomenon demonstrating these basic properties: extension property, universality, homogeneity, uniqueness. Another example I wanted to at least mention is the classical result of unison, the unison homogeneous metric space. There is a unique separable metric space U with the following property. Again, for every isometry between finite subspaces, there is an isometry of the whole space which we extended. This is again, this is ultra-homogeneity. On the picture, this is your Poisson space here. You have one finite subspace, another finite subspace. Between them, you have an isomorphism, and you want to extend this isomorphism to the automorphism of the whole metric space here. This is the property we are looking at. Yeah, and for uniqueness, it also contains every finite metric space. But just from these properties, you automatically get that the response in fact contains every separable metric space, not only finite but automatically separable. And this is also related to a countable version of that space. Namely, there is a unique countable ultra-homogeneous rational metric space, meaning that the distances in this metric space are not arbitrary numbers but rational numbers, denoted by Q. Such space, the unique space which contains every finite rational metric space. So like the same thing as above, but only for rational metric spaces. And it turns out that this big one is just a metric completion of this rational one. The point is that this countable one fits nicely with the classical Fraïssé theoretic setup, but for the full one, we would need something more, something like more. Yes. So these were like some three basic examples of classical structures. Maybe most of you already seen these examples here and there. The point is just to demonstrate these properties, just organize them in a more systematic way. And for that, we shall use the language of category theory. So just quick reminder about the basic terms and about the notation from category theory. So category, which we shall denote usually by some calligraphic letters like K, L, and C, consists of two things. You have objects on one hand, and on the other hand, morphisms between the objects. And the morphisms, which is something like function going from one object to another one, part of the structure is how they are composed, that you can compose the morphisms if the domain and the codomain of the consecutive morphism matches, and they are also identities. So you have one object and one morphisms which go to Y, then you have another morphism which go to Z, and then if you have pitch like this, you can compose them. This is the composition of them, and how you compose them is part of the structure. Yes, and like some classical. So the point of this is that it just allows you to abstractly capture various situations which you see everywhere. So you want to point the objects you are interested in: sets, groups, topological spaces, vector spaces, Banach spaces, whatever you are interested in. But also the class of morphisms, of structure-preserving maps between them, which you are interested in. If, for example, even if you fix compact spaces, you may be interested in continuous maps, or maybe you have metric and you want also the metric to be preserved. Maybe you want your maps to be surjective only. The point is that you just point out which object I'm interested in and which special functions I'm interested in. And the package I obtain, this is a single category. And I can abstract the various constructions in this abstract language and just apply it on any particular category I'm interested in. So these are just some examples. Here in classical Fraïssé theory, we are mostly interested in this category, which I denote by ENEL, the category of L structures and embeddings between them. When this L is the first order language, so we have some relations, maybe functions, constants, and I just, as objects, I take all my L structures, as all morphisms, I take all the embeddings. So all structure-preserving maps, which are moreover one-to-one, and they not only preserve the relations, but also reflect the relations. And we shall often actually consider a pair of categories One will represent something like small objects, the other one will represent something like large objects, usually denoted by K and L, which is just that you have two categories and one of them is subcategory, meaning that that picks only some objects from this one and only some morphisms out of this one. If it picks all morphisms between the special objects, it will be called a full subcategory. So in particular, if you remember the examples we were talking about at the beginning, for example, when we were talking about these rational numbers, here these small objects would be finite linear orders and order embeddings, and the large objects would be countable linear orders and order preserving embeddings. So this particular example would fit in this scheme we will be talking about this particular way. So everything clear completely so far? So now again, let us rephrase the properties we've stated at the beginning using this abstract language of category theory. So we were talking about ultra-homogeneity, which is defined by the ability to extend finite isomorphism. Every isomorphism between finite structures can be extended to an automorphism of the big structure. More diagrammatically like this. In the language of category theory, you can quite conveniently write it this way. For a pair of categories K and L, we say that a large object is homogeneous in this pair if for every small object and every pair of two maps to these large objects, there exists an automorphism in this large category which closes the triangle. This is just a slightly different version of that picture. Because in principle, the category doesn't care about inclusion. So it sees just embedding here, isomorphism here, and embedding there. So you just can take this here and just simplify it a bit and just review this one. So it's clear to everyone like that this picture really represents that you have like two different copies of X in EU, which are bound by some isomorphism, and you want to extend. Same thing. And I had something more. Yes, and like this notion is quite flexible because when we say classically, in classical sense, ultra-homogeneous, it says like for every finite substructure, or more generally for every finitely generated substructure. You don't have to say that because actually this parameter tells us over which substructure it is supposed to be homogeneous. So it is like fully general. You can put anything you like here to encode various notions of homogeneity. So in particular, structure is ultra-homogeneous if it is homogeneous over its age, over the class of all finite substructures of that structure. This is some standard model theoretic notion. So we've encoded ultra-homogeneity. Then there was this extension property, injectivity or injectivity. These are just synonyms. Which again, countable, for example, countable relational structure U is injective or has the extension property. If for every two its finite substructures, whenever you have embedding like this one and you extend it to something bigger, it can be closed. This extension can be all realized already inside of this structure. We can again say it more abstractly using the notion, using the language of category theory and using just abstract arrows here. Large object is injective or has the extension property if for every embedding of this small object into the large one and now this is important. This is again like small morphisms. This is a K-map. It uses the fact that we are in this small category. We can close the diagram. This is just more diagram. And then we were talking about this universality or cofinality. So this is just the ability to like contain everything you are interested in. A structure is universal for a class of structures if it contains every structure from that class. So more abstractly, again, we have this pair of categories, our setup, our frame. We say that a large object is cofinal if every small object can be embedded. There is a map from that small object into. So now we have all the basic definitions of the basic properties we are interested in. So what is this Fraïssé limit, or what is this general question? We have these two categories and an object, and we have considered these three properties: homogeneity, injectivity, cofinality, and we've seen that they often come along each other and somehow interact. So what is the general landscape? So it is always the case that if U is cofinal and homogeneous, then it is injective. This is always the case. This is just a simple abstract observation. You have your Fraïssé limit. You have an embedding of something small. You extend this small thing, and by cofinality, you can embed this Y again into U. And by homogeneity, we can close the diagram by an automorphism. So in particular, by this composition, we solve this injectivity problem. So this is like very simple abstract argument that says that this is always the case. But sometimes the opposite is case as well, as long as you assume cofinality. So sometimes it is the case that this special object is cofinal and homogeneous if and only if it is cofinal and injective. Sometimes it is the case that such U is really a unique, there is a single object with this property, if it exists at all. And sometimes such object is actually cofinal not just for the small ones, but even for the large ones. And if this is the case, if really the system behaves in this nice way, this is everything consistent together, then it makes sense to call it the Fraïssé limit. And now we shall discuss like when it is the case and what are the general theorems stated in this abstract language. So for that I need yet another bit of abstract stuff from category theory. Let's recall what is a sequence, or more precisely a direct sequence in the category. It is just a sequence of objects together with sequence of morphisms between the object, such that this notation is like notation also for all the compositions among these systems. And there is this standard notion of colimit of a sequence. So abstractly, colimit of that sequence in a category is yet another object x infinity together with a family of maps like that, such that all these triangles are commuting, but this composed with that thing is the same thing as that thing. Such thing is called a cone, or a cocone, in this case. So you have the object, you have the cone, and it is a colimit if it has the universal property. So if someone gives you some other cone, then you have the unique factorization map going here. Given any other cone, there is a unique map such that all these triangles are commuting. Like depends on your background. Either this is very trivial to you because you've already seen you know the category theory, or you haven't seen it at all, and then it looks like what does it even mean? So a very specific example to have in mind is that in these very concrete structures, so when these objects are really structures, so it's just a sets with some maybe relations, functions on top of them, then such sequence is without loss of generality just an increasing chain of structures. You have one structure, a bigger structure, which agrees structurally with the smaller one on the smaller set, and so on. And in that case, the colimit is just the union of this chain. So the structure whose universe is just union of these sets, and all the relations and functions here, since they depend only on finitely many points, are already determined by the finite thing. So is this clear? Like your seminar, you can just ask question or point something out, no problem with that. So we need this bit. So
did you say that the sequence is really a functor?
I didn't, because I didn't yet say what is a functor.
Because this is shortcut way.
Only if you know what is a functor. Yes, but you are right. If you know category theory, then you can say, yes, sequence is just a functor from omega when viewed as a. Okay, so we can build, or possibly we can build limits of sequences. And now I just want to give just an intuitively explain a notion called free sequential co-completion of a category, or just free completion. This is when we have this pair of categories, this setup we are talking about, which is like very nice. This is like a natural collection of conditions in which all these, under which this basic Fraïssé theoretical setup really works just like this. So abstract or like intuitively, you can say that this pair of categories, like one smaller, one bigger, this pair is a free completion if it satisfies such some conditions, which essentially say just that these large objects essentially arises as freely adding colimits to the sequences. So the large objects are just limits of the sequences which you've added in a free way. You didn't like
countable sequences.
Yes, countable sequences. Yes, all the sequences in this talk and all the core of this theory I'm talking about is about countable sequences. It's not the case with the next talk. Yes, we need to do some uncountable stuff. Yes. So, like the nice idea or the intuitive idea is that it means that free addition of colimits, precise definition will be later. The point is that it gives you nice correspondence between countable sequences of small objects and large objects. Not only that, like every sequence of small objects give you a large object as limit, and every large object is a limit of such sequence. But moreover, there are some nice conditions between them, something called factorization conditions, which on one hand make the proofs in abstract Fraïssé theory work, but in fact this on itself is like very natural and actually very standard notion from category theory, which are realized at some point. First for us it was like, yeah, these are some nice conditions which make the theory work. But yeah, actually this is something which makes sense abstractly in category theory. So this is something very nice and stunning. The point is that in the classical setup, when K are really finite structures, relational for example, and L are their countable unions, these special conditions are met. They are just true. So in the classical Fraïssé theory, when people are really working about with finite structures, countable structures in relational languages, they don't care about them because in that setup they are always true. But if you want to prove the general results in this setup, you need to exactly point out what you are using and check that it is true. Okay, so we talked about sequences, and now let's recall what is a Fraïssé sequence. So a sequence in a category is called Fraïssé if it is cofinal and injective. So cofinality of the sequence means that you have the sequence of small objects. And cofinality means that it contains every small object. For every small object there exists an arrow to some point in the sequence. And this injectivity, this extension property, says that whenever a small object already is included in the sequence and you somehow extend it by a small map to a bigger small object, then you can move this object again to the sequence such that this parallelogram is commuting. In fact, like these conditions, this is really analogous to the definition of cofinal and injective object, like when we are talking about large object over the category, when we are talking about this extension property. The point is that these notions of cofinality and extension property are somewhat general, so you can really define them for every think over a category, whatever it is, a large object outside of the category, or is it a sequence or some diagram in the category, or completely generally something called pre-sheaf over category. So like you can define them specifically for sequences, for large objects, but all the definitions are analogous and in fact are special cases of something more general. Like intuitively, it is a sequence which is rich enough so that it absorbs and realizes all the complexity which happens, which occurs in. So, what is the time? Okay. So we were doing this back and forth construction in this very particular case. Let us quickly show us the core of the proof of one of the basic theorems of the theory, how this back and forth argument works abstractly. So suppose we have two Fraïssé sequences in our category. So we have one Fraïssé sequence, and another Fraïssé sequence. And suppose we are also given a small object and two embeddings of it into the sequences. Then we can find a sequence of maps going like this, such that all these triangles are commuting, which in the end will mean that there will be a limiting map of all these arrows going this way and a limiting map of all those arrows going that way, which turned out to be mutually inverse isomorphisms. Moreover, commuting with this. So you just apply the definition of the Fraïssé sequence. You start with this. You know that this sequence has this injectivity property, which means that you can, from this object, find some map like this, such that this is commuting. Then you apply the same thing for the other sequence. I have this extension, which means that I can go back such that this is commuting, and then you continue. So in a sense, it is the very same thing we are here doing, really just with points and functions in Q, but said in much more abstract language. The key idea is still the same. And in the end, we obtain these limiting maps just by standard abstract nonsense of the category theorem. Like if you wanted to show, I mean, if you take all the maps going like this and compose them along the sequence with this column in here, it will give you a column from this sequence to this object. But you already have the column, the canonical column. So you know that there is this unique map going like this, such that it is commuting with all these maps. And you can do the same thing the other way, and also for their composition. So you will show that this is identity and that is identity. So they are two mutually inverse isomorphisms. And moreover, this thing, if you go like this and this, it is commuting. So this in particular shows you this is the same proof, the same back and forth construction. Both give you uniqueness of the Fraïssé element and the homogeneity of Fraïssé element. Because uniqueness, because you may start just with two Fraïssé sequence, and here put anything, just take any object, and by cofinality you know that there is some map like this and there is some map like this. And in the end, you just show that, yeah, we have isomorphism here, so the Fraïssé elements are isomorphic. And homogeneity means that you already started with something like this, and you are able to close the diagram. That's the homogeneity. Well, almost. In the definition of homogeneity, these maps didn't go to the sequence, they only went to the limit. To get them into the sequence, you first need to factorize the map through the sequence. You need to know that whenever you have a map from a small object to the limit, then it actually comes from a map like this. And this is one of these extra little conditions in this definition of free completion, which make it work. So this is like just a sketch of the abstract argument. So everything clear? So now we can formulate compactly, essentially all these basic abstract Fraïssé countable theory, essentially in two theorems. So we have this theorem, which is the characterization of the Fraïssé limit. It just says, whenever you have this pair of categories, which is a precompletion, and you have an object, then the following conditions are equivalent. It is cofinal and homogeneous, if and only if it is cofinal and injective, if and only if it is a colimit of a Fraïssé sequence in K. Moreover, such U is unique. It is cofinal not only for the small objects, but even for the large objects. And moreover, not only that it is a colimit of some Fraïssé sequence. Whenever it is a colimit of any sequence, that sequence also has to be Fraïssé. So whenever you have a sequence and a limit, this is a Fraïssé limit if and only if this is a Fraïssé sequence. So everything really works nicely as one would hope, but you need to have these conditions. So everything works nicely. This is one of the founding theorems of the abstract field. Also know that this is just like a uniqueness and characterization. It doesn't tell you that it exists, but it reduces the existence of such object to existence of the sequence. So such object exists if and only if in this category of small objects the Fraïssé sequence exists. But now we can talk just about a single category. We can have just a single category K and ask when it has a Fraïssé sequence. And that's like the other theorem, the existence part of the setup. So when does the sequence exist? It exists if and only if K is so-called Fraïssé category, which are the following conditions. It is directed, or in a classical sense, when these maps are embeddings, it is called the joint embedding property. It just tells you that whenever you have two small objects, you can both map them to single maps. The second one is the amalgamation property, which tells you that whenever you have two maps like this, called span, then you can also find an object and a map like this, such that this square is commutative. Amalgamation property. And you also need another thing, you need at least a bit of countability in the category. Not necessarily that the category is really countable or that it is essentially countable. You just need something smaller inside which is countable and rich enough. Maybe I can skip the details for now, but it often happens that K is actually locally countable, meaning that between every two objects you have only countably many different errors, or even locally finite. Like if your structures are really finite sets with some structures and your morphisms are really functions, some special functions, you have just finitely many of them. So this bit is easy. And the other part of it is that you have maybe only countably many types of structures. You have only countably many finite linear orders. You have only countably many finite graphs up to isomorphism. But so this is like conditions which are typically stated in the Fraïssé theorem and which are often true, but they are stronger than what is needed. This dominating subcategory is not only enough, it is also necessary. So this is really equivalence. So these two theorems, the characterization of the Fraïssé limit and the existence of the Fraïssé sequence, this is it. This is like the abstract setup, abstract countable discrete setup. And that's essentially the whole theory nicely packed into two theorems. Okay, I wonder to what extent I want to go to the actual definition of this free completion over there. Maybe just like I stated most of them. So you have the pair of the categories: small things, subcategory of large things, and free completion means four things. First two things are very easy, as I said. Every small sequence has a large colimit, and every large object is a colimit of a small sequence. So far, so good. But then you have this factorization property. Whenever you fix a sequence, and its colimit, and you have a map from a small object going into the colimit, then there is actually a map already going somewhere to the sequence such that this is commutative. Concretely, this is true, for example, for finite structure. If this is increasing chain of finite sets, and this is its union, the countable set, and you have a finite set contained in this countable increasing union of finite sets, it's already contained in one of those finite sets, right? This is trivial in this particular case. Nevertheless, it is something you need to state on this abstract level and something you need to have if you want your arguments to be true. And there is like, this was like existential part of the factorization, and this is like the uniqueness part of the factorization thing. Whenever you have two maps from a small object, which are equalized at the limit, then they were already equalized before reaching the limit. Actually, usually you get this condition F2 quite easily because whenever your category consists of so-called monomorphisms, so from something like one-to-one functions, embeddings, which means that you can cancel actually everything from the left, then this F2 is trivial, so you don't have to care about it. So like the least trivial condition which you sometimes need to check is this factorization. And by some general category theoretical results, actually, if you start with some small category, you can always build this larger thing, which is its free completion. And moreover, you can do it essentially in a unique way. Here we define it rather as a property of a pair of the categories. But it is also a construction. You can start with something small and essentially uniquely build the large thing. On the other hand, this large thing has colimits of all sequences, not just the small ones, and contain this K not as just some subcategory, as a full subcategory. So between two small objects, large morphisms and small morphisms are the same. So these are some technical details regarding this free completion thing. Now let me give you a couple of comments on how to get such free completion. So so in the classical case, you just have it. If you fix a first order language L, and by F you take your favorite class of finitely generated L structure, and morphisms will be all embeddings between them. This is important. And by sigma F, this should be sigma F, that's a typo, should be the class of all colimits of F sequences, so all structures which are unions of countable chains from your class, which are some countably generated structures, again together with all embeddings between them. Then this pair F and sigma F is the free completion. So in this classical case, the conditions are always satisfied, and that's why they are not explicitly pointed out like when you are doing preset theory classically with structures in model theory. So this covers some of the standard situations. Yes, but now I want to make a step aside. So the point, so we've started with some basic examples and then like build some like general abstract theory, even though it is just two theorems. The point to use this abstract language is that it covers like many different situations. It doesn't have to be structures and embeddings. It can be really anything which satisfies this axiom. In particular, it can be these examples from so-called projective Fraïssé theory. Namely, the simplest example is that E consists the opposite category of non-empty finite sets and surjections. So our objects will be just non-empty finite sets, and our morphisms will be surjections between these finite sets, formally going the opposite way. So a morphism from X to Y is really a surjection from Y to X. then there is this opposite business, so it formally fits. You can actually, just by self-duality of category theory, do the whole theory opposite, just reverse all the morphisms and it will be the same theory. The point is that in a classical situation, you have small structure and more complicated structure is a bigger structure in which this one is embedded. In the projective case, your simple structure is something small, and the more complicated one is one which is projected back on it. You have like a quotient map going the opposite way. Yes, so if you take this particular category, so your objects are just finite sets. Your morphisms are just continuous surjections. This is your category. This category is nice. It is a Fraïssé category. It is essentially a countable category. There's amalgamation property, everything. So it is a Fraïssé category. It has a Fraïssé sequence. In fact, you can very easily say what is a Fraïssé sequence in this category. In this category, your sequence is Fraïssé if and only if every point splits eventually. So you are in your set x2, let's say, you have this particular point, maybe in x3, only one point gets mapped to it, but eventually, in some set x100, you take a set x101, it will have more pre-images. This function going here would glue 2 points to this one. So this point eventually split it here into 2. If this happens for all of these points, this is exactly when the sequence is Fraïssé in this category. But now regarding to this notion of free completion and a Fraïssé limit, the question is like where to take the limit? What should be the free completion? Like obviously you can make an inverse limit, but what kind of inverse limit? If you view it merely as sets, if your large category will be just profinite sets, so exactly sets which you obtain as inverse limit for these together with all surjections, then this thing is actually not a free completion and there is no Fraïssé limit in this category. Namely, the extension property would mean that whenever like the limit would be like a Cantor space actually, but viewed just as a set. But it is not a Fraïssé limit because you can have a function onto something finite, so some partition, but extension property which essentially tells you that every partition can be like every equivalence class of every partition can be split into more points. As at least 2 points can be split. But if it is just any partition, you can always take a partition which contains just some singleton set and then it can't split. But if you take topology into account, which on one hand is very, very natural in this context, we want more rich structure. So if your category will be not these things used as sets, but rather as topological spaces with the projective topology which you get. So the metrizable compact zero-dimensional topology you obtain from the inverse sequence, and your morphisms will be only continuous surjection. Then this is a free completion, and the Cantor space is the Fraïssé limit, because then your finite partition can be only a Claudian partition, and so its equivalence classes will be big. It will be again copies of the Cantor space. You can't have just a single point there. So in principle, not only that, like naturally wants to consider topology here, but you have to, otherwise it doesn't fit into the theory. It would be like a wrong choice from the point of view of the theory, and you couldn't apply the theory. So this way you can obtain the Cantor space also as a Fraïssé limit. And more generally, this is something called projective Fraïssé theory, which was introduced by Ivan Soletsky. So it is a projective counterpart of the classical injective one, where you have a first order structures and embeddings. Here you have rather first order structures and projections, and the quotient maps going the other way. So this example with the Cantor space would correspond to like empty signature, no extra relations, no structure. So just countable sets and inclusions, but here finite sets and projections. So in that case, if you fix, let's say, a relational first order language, and your category will be a category of so-called topological L structures. So it is an L structure, but you also have profinite, so compact zero-dimensional metrizable topology on it, such that the interpretation of the relations are closed. They are closed sets, and your morphisms should be quotient maps. Quotient both with respect to the structure, to the relation, but also with respect to the topology. And then you take the full subcategory of finite such structure as being the small things. Then this pair is a free completion with respect to the definition. So this projective price set theory formula fits into the setup. So just to give you some examples, most of them we need covered. Some examples of these categories and of their limits. We already talked about linear orders and the rationals being the limits, graphs and the random graph being the limit, the metric spaces and the Guruson space. These were the three examples at the very beginning. There is also, for example, something algebraic, so finite groups. You don't get all countable groups, only locally finite countable groups. There is something called Hall's universal group, which is the Fraïssé limit in this case. So these were on the side of the embeddings, on the side of the classical Fraïssé theory. In the projective Fraïssé theory, we mentioned this Cantor space as being the Fraïssé limit of just finite discrete spaces. And like the first non-trivial example, which was in this paper by Emil Solecki, who built this theory to actually do this, is when your small objects are finite discrete linear graphs. And then as a Fraïssé limit, you obtain pre-space of the pseudo-R. So essentially the Cantor space, together with some special equivalence relation gluing pairs of points here and there, such that if you take the quotient, you will obtain the pseudo-R, which is some very complicated structure from continuity theory. Okay, so let me just quickly go through another thing. The point I wanted to make that, for example, the classical theorem by Knaster and Reicbach, giving you a better injective homogeneity in the Cantor space, namely that whenever you have two homeomorphic closed nowhere dense subsets of the Cantor space, and you have the homeomorphism between them, you can extend it to the homeomorphism of the whole Cantor space. That this result can also be like viewed as a consequence of this abstract Fraïssé theoretical stuff. But you need to make a little trick. You need to take some special category, not like some injective or some projective one, something else, something called comma category. Namely, you fix a single compact zero-dimensional metrizable space K, and your objects in the category will be actually maps from that fixed one to another one. So an object is a continuous map from your fixed object K to some finite discrete space XF. And the morphism between these two objects, so this arrow is actually an object here, the morphism will be yet another arrow surjectually here, such that the triangle is commuted. So constructions are like this are sometimes called comma categories. So if you take this particular category, then you can show that it is a Fraïssé category in the abstract setup, and that the Fraïssé limit, which should be again some map from that fixed object K into something, is in fact an embedding of K to a nowhere dense closed subset of the Cantor space. And whenever you take any embedding of K onto a nowhere dense subset of the Cantor space, then it is a Fraïssé limit. It satisfies the properties of the Fraïssé. It satisfies the extension property. Therefore, it is a Fraïssé limit. And therefore, just by abstract uniqueness of the Fraïssé limit, you obtain the Knaster-Rybach's theorem. Because then you would have, if you have these two closed, nowhere dense sets in your Cantor space, which and the homeomorphism between them, it is that you have these two objects, K embedded into the Cantor space one way, K embedded into the Cantor space the other way, and they are both Fraïssé limits, both objects of our category. By uniqueness, there is an isomorphism between them. And this isomorphism is exactly an isomorphism of these spaces, making the triangle commuting, so it gives you exactly the homogeneity issue. So to wrap it up, all the thing, I just wanted to give you some quick overview of the same thing. So first thing, there are these interesting properties which you can see here and there, namely the homogeneity, the extension property, and the universality. You can really find them in the wild. You can see them in various structures, like rationals, random graph, Eurison space. But you can build this abstract theory about them, which in this setup consists just of these two theorems: the characterization of the Fraïssé limit and the existence of the Fraïssé sequence. And third takeaway is the idea that using categories and the language of category theory makes the theory flexible. So it covers many situations, not only the classical ones, also the projective Fraïssé theory, or, for example, categories of embedding projection pairs, these comma categories, which then allows you to arrive things like Knaster-Rybach theorem, or categories of partial automorphisms, when you want to talk about existence of conjugacy classes in automorphism group and stuff like that. Formally, you consider a category, and you can build, you can consider this abstract theory. So that is just like the quick message I wanted to give you. So that's all from me. Thank you very much.
Thank you. Questions, comments?
So I guess you will then make the slides available on your page, right?
So please send the file with the slides. Okay, I will stop recording at this point. How long break would you make? Yes. How much?
Depends. If you want to finish on time, you can make a short break.
10 minutes.
10 minutes.
10 minutes.
10 minutes.
Okay. And I think we can extend a bit because